Hi, Keith here with another statistical video, and this is one I've been meaning to do for some little time, and you can see by the title of this paper basically what this little talk is going to be about: the homogeneity assumption for analysis of variance. The assumption that the groups being analysed have approximately equal variances. Now, I'm using some dummy data that you can see here in the table on the left. The observation's black on blue, so there's 3 treatments, each with 10 replicates, and equal numbers of replicates is the best case scenario for analysis of variance. And then you can see in the white boxes the ratio of means, 1 to 2 to 3, and same for the variances. Now the observations here are being generated from a log normal distribution, so the numbers down here don't come out in that nice 1 to 2 to 3 ratio. What we can do, and what people may be in the practice of doing, is doing a Cochran's test. And Cochran's test is the largest variance, so variance for group 3 here, divided by the sum of all variances. And because that third group, which I call control 2 for no particular reason, that third group variance is 6,500, it overwhelms everything. The Cochran's value calculated is 0.95. That's nearly the maximum value, which is 1. And the table value is 617, so calculated greatly exceeding table, the variances of the groups are not the same, which is pretty obvious from looking at the numbers. Now, I said the data were generated roughly from a log normal distribution, so if we take logs, that should fix things out a bit, and over here it does. So the variances come down much more similar. Now, they're still not equal, but the difference among the 3 is greatly reduced, and according to the Cochran's test, the variances are okay for the analysis of variance. Now, we'll come back to that point a little bit later. Now, let's get into it with the analysis. So over here, I've taken the data into Minitab, reorganised in the standard format, so the 3 groups, and I've already done the analyses. So here's the one-way analysis, and the FA is 5.82.008. Now, of course, we have a problem here. The data obviously do not fit the assumption. So is it safe to proceed? Can we trust this result? Again, I'll come back to that in a moment. What we have seen from the Excel demonstration here is if I do a log transformation, the situation is much better. So back here in Minitab, 5.82.008. If I do this on the log data, the FO becomes bigger, the p-value becomes smaller, and this is a result which, according to Cochran's test, is reliable. Well, why do I keep saying according to? And this paper, which I wrote some time ago, was looking at 2 test procedures, Bartlett's and Cochran's, which aim to tell you whether or not it's safe to proceed with an analysis of variance. Now, that's only 2 of quite a few. So in here, I did a little summary of what was recommended, and you can see aside from Bartlett's and Cochran's, there's also the Fmax and Levine's quite commonly, but there are a few others. Very commonly these days, Levine's test is included as an option. Back when I did this, it was only starting to be used. So now here, Table 2 and Table 3 are the basic guts of this paper in terms of the results. So let me look at what I've got over here on the left-hand side for alpha equal to 0.05, so that's standard 0.05 significance level. And if you read the caption up here, what I did was simulations with k equals 3 means. So exactly the same as the one I've shown in Excel, and in Minitab there were 3 groups. And the second letter results here is for n equals 10 observations per group. And you can see started with 3 and worked through to 37. Now, what's in the table here? Let's look at the column 1, because for that column the variances for all the groups were equal. And what I'm looking at, or what I've shown here, tabulated, is the percentage of tests that were significant. So for each simulation, and I can't always remember how many I did, it'll be somewhere, probably about 1,000. For each simulation I checked first whether Cochran's test or Bartlett's test was significant, and then I went and did the analysis of variance and checked whether or not that was significant. Now, if all the variances are equal and the null hypothesis is true, which it is for these data, the means of all the groups were equal, then we should get about 5% significance tests for all of the tests. And in this column mount here, you can see that's the case, varying from 4.8, 4.4 up to a bit over 5, occasionally 6. Over here in the 0.01, the value should all be around 1%. So the simulation is working as it is supposed to do. What about Cochran's test and Bartlett's test? Well, first thing here, 1 over 81 means one of the variances was very small and the others were equal. We go through, as I said, to the case where they were all equal, and then one variance was 3 times the others, and then one variance was 81 times the others. So what happens? Well, let's start with the 81 columns, because that's clearly a case where one variance is much larger than the others. N equals 3. Cochran's test and Bartlett's test are significant most of the time, 3/4 of the time. That's good. N equals 10 and onwards, Cochran's test and Bartlett's test are always significant. But have a look at the F ratio. Varies from 8.4 to 14.3. In other words, once you get to n equals 10, Cochran's and Bartlett's tests are telling you there is always a problem, whereas often there isn't. And you can look through all the results here, and that is the conclusion pretty much all of the time. Scroll down here, these results were just done using 5 means, so this time there was 5 groups instead of 3. But otherwise the conclusions are pretty similar. Once you get to a reasonable number of replicates, Cochran's and Bartlett's tests say there's always a problem when often there isn't. Now, what's going on here is relatively simple to understand once you start thinking about it. Cochran's test and Bartlett's test are tests of a null hypothesis, and that null is that the variances of all the groups are equal. All statistical tests depend for their power on the number of replicates, so the more replicates, the more powerful a test. What this means is that if you have a reasonable number of replicates, which in these simulations is 10, then Cochran's and Bartlett's tests become overly sensitive, and they lead to rejecting that null and saying the variances are different, there is a problem, far too often. Cochran's test and Bartlett's test are far more significant, far more influenced by variance heterogeneity than is the analysis of variance itself. And the case is especially severe when one of the variances is very small, especially for Bartlett's test. Bartlett's test says pretty much says there's a problem all the time. Cochran's test says there's a problem some of the time, but look at the F ratio. It hardly budges from 5%. Small variance, one small variance does not affect the analysis of variance at all. And a moderately large variance doesn't bother it greatly either. It's only when you get to very, very large variances that there starts to be a bit of a problem. But it's still not as large as these tests would suggest. Okay, so what do we do? Well, what you may see people starting to do these days is switch to looking at residual plots. Now here are the residual plots for Minitab for the untransformed data. And there's three things to look at here. Top two plots and the bottom left. I'll talk about the bottom right, but it's often not important. Top one is normal probability plot, and if the observations are normally distributed, they should fall pretty much on a straight line. Clearly they don't. There's a big bend going on here. Here is basically looking at the residuals. So the residual is an observation, take away the mean for the observation, so you get positive and negative residuals, and they'll balance each other out. The fitted value is the mean for the group. So you can see that as the mean goes up, we've got this triangular thing happening here where the variance gets much, much bigger with increasing size of mean. Histogram here is just a histogram of the residuals, and we're looking for something more or less normal, roughly unimodal. And that's not happening. We've got a bit of a skewed distribution going on here, with most of it down here and then some very high values. Here is residuals plotted against observation order, and this is of importance if there is some time sequence, some temporal sequence in the way the observations are collected, because if some odd pattern is going on here, you might be seeing a change in the accuracy of the instrumentation or some sort of observer bias. This is not relevant for this set of data. Okay, let's go to the log transform data, and things are looking quite a bit better. There's still a bit of a trend going on here, so the transformation hasn't removed it entirely, but it has greatly reduced the difference between this group and the other two. The points are now falling mostly along the line, and the histogram down here is looking much more normal. So based on this, I'm happy with the analysis of variance results. I will comment that there is a point sitting down here and one sitting over here, and it's down here, and that looks to be a bit of an outlier, so I'd be going back and looking at that. Now, transformation is one way to proceed. It's a standard way to proceed, and if it works, there's really no issues. The way I deal with these issues now is something different. Here I've moved them all, the data, into Primer, and in Primer with PermANOVA add-in I can do a permutation analysis of variance. So I've created the design here, which is just one factor, which is fixed, and to do the analysis I select the variable I'm interested in, select highlighted. I then create the resemblance matrix using Euclidean distance. Okay, Euclidean distance, that's critical if I want to do the PermANOVA on a single variable. PermANOVA, incidentally, if you've looked at the other videos, is designed for doing a multivariate analysis of variance. But if I use Euclidean distance for one variable at a time, I can run a permutational analysis of variance So if I go in here and start the Perm ANOVA, it has picked up the design sheet I want, design 1 for group, and the recommended method here is unrestricted permutation of raw data for one factor. Everything else is left the same. And here's the results. So if you look here, the numbers in here are the same as we get with Minitab. The F is 5.82. Let's go back. 5.82, 90,036 is a total sum of squares. 90,036 is total sum of squares. So all that is the same as doing the conventional analysis. What differs here is the p-value. It comes in Perm ANOVA from randomly permutating the data, however many times, and calculating the analysis of variance and recording the F values. So out of 1,000 possible F values, a few were larger than 5.82, but most were not. So the calculated F value there is extreme and it is significant, 0.03. What did we get for one-way ANOVA? Conventionally, 0.008. I think I just said 0.03 for ANOVA, it's 0.003, 0.008 here. So Perm ANOVA and the conventional calculations give us very, very similar p-values. And I've done this lots of times now, and it's always the case. The only time it doesn't work out is if it's a complicated model with random factors, where Minitab and Primer sometimes use different ways of calculating the F value. If you've jumped ahead, you'll know I've also done the analysis on the log transform data. Basically the same results coming out here. The F value gets bigger and the P value gets smaller. So regardless of how we do the analysis, we get the same conclusions. There is a significant difference among the groups in their mean. Now, I would need to explore that further to work out what that means, but this is random. This is simulated data, so it's not much point doing that. The advantage of doing the permutational ANOVA is that it dispenses entirely with the assumption of normality. No particular distributional assumptions are made in terms of the shape. There is an assumption about, rough assumption about similarity of dispersions, which is equivalent to the analysis of variance, homogeneity or variance assumptions. But it's weaker, and I can also test for that by doing permutational analysis for dispersions. And if I do it for the untransformed data, the permutational analysis says 0.001, highly significant difference among groups in terms of their dispersions. If I do it for the log transformed, 0.162, not a significant difference among dispersions. So the log transformed results are reliable either in Perm ANOVA or in Minitab ANOVA. The untransformed in Minitab may be suspect, and that might be the case here, but remember I've set up a situation here where there is extreme difference in the variances of these groups. Extreme. 1.5 up to 6,500. You won't see anything like that in the real world. Okay, hopefully that helps. Some understanding of variance homogeneity and the analysis of variance. One thing before finishing, I'll just go back here. One thing that analysis of variance is sensitive to is independence among the data. And so if there is some temporal sequence and something funny going on here, That is something you have to take rather more seriously, because that will certainly greatly affect the reliability of conclusions. It may, non-independence can increase type 1 error rate or drastically decrease it depending on the type of non-independence.